Actually to hear an interesting talk from Dr. Obudai Chatterjee. He is now a young senior researcher. He did his HS from Katwa Kasiram Das Institution and then did his BS and MS from ISER Kolkata. Okay, and then did his PhD from University Paris at Marie Curie, France, and now at postdoc at Laboratory of Plasma Physics, University de Mons, Humans, Belgium. Okay, and working on plasma physics. And he will talk about the journey of physics, how to be a physicist. So I think, or I all looking forward to hear some interesting things about physics, journey of physics from Obudai. So Obudai, please start.
Thank you, Rajesh. So here I am here to just discuss a bit about like our journey. It's like I really found it will be interesting for you all students who are now studying physics as their mainstream subject. But I don't know like. At some point when I was doing my bachelor's and master's, I felt like, okay, so I'm going to do my master's in physics, but why shall I do it? Like, why do I do in physics? So here I'll tell you basically a story of the cool people you all know, and like who are physicists. You have heard some names. We'll call some names, and at some point we'll just discuss like how the flow went through. Um, so let's hear it as a story, not some serious thing. Let's hear a story about it. So first, I want to thank Physics Department of Ramakrishna Mission Vidya Mandir and of course Rajesh for inviting me to talk. And of course, if you come to a research field, you'll know like acknowledgement is important because that's how we progress to continue our previous work and follow through and take it to another level. But I took all the ideas from the Google and of course pictures from the Google and Wikipedia. So let's continue our journey through how it evolved. So already Rajesh introduced you how I did all the stuff where I did it. To briefly tell, I completed my school. Then I was like, I have to go to general science. I don't know, maybe physics or maybe biology. So that's how I entered ISER Kolkata, which was very new at the time. Then I continued my PhD in Sorbonne, and I did my PhD in Sorbonne. Then now I'm doing postdoctorate. So then in this journey, I realized like how to do physics. So in this presentation, basically I'll show how it evolved. Not only that, but how I see how the physicists start to be. So when first you think about being a physics student, what comes to your mind? Like if you tell any person outside your field and who are doing other stuffs, they will be like, you are so smart, you are doing physics. But is that it all about? Even for science, like you'll hear people say, the first thing you say you are a scientist probably comes with a lab coat and goggles. But I don't think now physicists are like that. Like they can roam around with some jeans or whatever, and like you'll not realize he's a scientist. So that doesn't count as scientist, like whatever society thinks of us. But so that then like what's physics? So when you are studying physics, what do you do? First, you learn about lots of theories of physics. Then you solve mathematical problems. You do some experiments, of course. I'm an experimentalist, so I'll say That's always the best thing to do in going to a lab and doing some cool stuff, maybe with laser, maybe with some other stuff, and some nice oscilloscopes and all these things. So it's always nice to do. But is it all about like solving mathematical problems of physical world? I don't think so. So this is the story, what I realized and what I think. So this is the picture of Newton. We all know this story. So suddenly he got hit by an apple which fell from the tree, and he came up with the idea. So there is gravitation. Earth is drawing everything towards it. Why not sun drawing the Earth back and all? And then he gave a formula like we all read: F is equal to my gmm by r square, and that's it. But then few years ago, I suddenly realized like, where did it come from? Like my gmm by r square, what does it even mean? You cannot suddenly uh, do something and say, okay, this is the formula. Even for gravity, you cannot even do an experiment in the lab to check if the gravity is working on the things, because Earth is so huge. By now we know that the mass is big, so on Earth everything will be controlled by the Earth. But how did he realize? So actually there are lots of history of going to that point, and that's when he realized, okay, this is the theory. But why is it like gmm by r square? What does it mean? If there are two particles, first they have to be particles. If there are two particles, so their attraction force will be determined by the formula gmm by r square. I wrote it in this form because um, of this minus sign, and it's interesting because if you know it's a force, so it's a direct, it has a direction. You know already about vectors, so it has a direction. And I intentionally put the minus sign to tell you that a gravitational force, when a body attracts towards you, so it's kind of attracting you towards the force, so we conventionally put a minus sign. And now you can ask me like, oh, can you put actually plus sign and put gmm by r square? Yeah, you can. Like, it's up to you. If you follow the notation towards the force or opposite to the force, it's up to you. Now this minus sign is important to know that, okay, so this force is directed towards the body. And why divided by r square? So if you think of a particle and if it expands uniformly from a particle, from a point, then all the symmetry we can come up is like a spherical symmetry. So if you take a small sand and somehow can expand, then it will go to a ball which is spherical. So if you want to distribute something on the surface of this ball, what is the formula? It's like 4 pi r square. So if you want to distribute something, if it's kind of like conserved, if you can think, then on the surface it will be distributed by 1 by r square. That's why this 1 by r square formula is actually, you can see it also in Gauss law, the 1 by r square thing. So these are the inverse r square forces that are there in nature, and kind of heads us to the conservation of energy and conservation of energy. So that's really interesting what I found. So now we have all the equipments in our lab to determine all the sophisticated things. So I work with plasma. So I measure gas temperature with something that if you say to an ancient human or even some animals, they will be like, what is this? And they won't care. But then like I try to think, where did all this come from? Like if I measure with an oscilloscope a small thing, and what do I realize? How do I realize it? And where has it been? So here we'll try to see how human actually created things and realized things. So first things actually started when tools started to be prepared by ancient human. They started to build wheels, tools, create fire. They were saving their lives. And then suddenly they started to communicate. They started to recognize other people. They started to recognize things that are appearing. Usually they had fear of survival, but at some point they were like, oh, okay, now we can actually continue as human. And then with the communication they started, that's a very impressive thing, like no other animals actually do, that human can actually store things. So if you imagine like an animal, it usually comes to life, dies, and the whole memory is over. But for human, it's not. So human stores the memory of previous experience, and you have an archive, and that's why we are different from other animals, and that's where we shine actually. That's why we are the best. So with all this, humans started to store history, and this history actually progressed us so far from other animals. Just to introduce you something, I'm also a bit interested in seeing the religious scripts of India. And if you see the religious scripts of India, and now you'll see like, ah, okay, we are in science. Why will we be interested in religion? Religion is also a part of humanity and its development. So if you don't understand what they feared, like in the beginning they feared of thunder, so they either came up with Indra in our religion, or Thor in Greek philosophy. So ultimately they feared something, and they said, okay, there are some supernatural powers that is controlling, so we feared them, and that's where things come to place. But then some people said, no, I don't think that's the only thing that's happening, and then the conflict begins. But then I tried to understand, okay, so really all the religions actually try to say, okay, we are created by some I don't know, four-handed, five-legged, or three-eyed guys from another universe or something, or what is the reality? Then I found this super nice part, which is a part of Rig Veda, which basically says we actually didn't exist at all. Nothing actually existed, and we came from nothingness. So we'll come to this part in the progress of our science, but I was really surprised to see that it was mentioned, like even if we have concepts of heaven and all and gods, we still said like at least these are created by some philosophers, I think, and they at some point realized, okay, the things actually came from nothing, and without proper scientific tools that we have developed by now and all, it's really something surprising to realize that we actually came from nothing. Nothing existed. Even the heavens apparently didn't existed according to this theory. And if you read it a bit further, it even says, uh, who knows who created this thing? Maybe even the Almighty God, he doesn't even know how this all came from. So actually, if you compare it with the modern theories of physics from where we came, this kind of resembles the philosophy that we had at some point. So it was very surprising for me. So I really thought this is worthy to mention, because it's the Vedas are very old. It's like 1200 BC and even older, and people started to think of where we came from. So this thing actually continued, and like the philosophy is well related to science, and if you see the old scientists, ancient scientists, they are mostly philosophers because they tried to think with the old history and observing the nature. They tried to realize what's actually going on. So the if you know the term PhD, which is philosophy, yeah, doctor of philosophy, a Greek word. So that's actually doctor of philosophy. We don't say doctor of science. That's kind of interesting, I thought, and I put it here. So where did it start? The first known scientist on Earth uh, can be attributed to Thales. So he was the first guy, at least in modern world, like which is mostly determined by how the Western people think, kind of. So because they kind of dominated over the world with the modern science and all. So we'll know a bit of Indian history, Indian science history too. So he came up with the idea, no, I'll not agree to whatever we have faith on, and like we are not created by this supernatural phenomena, and we are we want to know what's actually happening. And from this urge, actually science started. Later on in Greece, a lots of people started to culture this practice. So what they tried to realize is, what does these physical things mean? And that's where the journey of science actually starts elevating. So Leucippus and later on his disciple Democritus actually were really the two main first people who started to believe, okay, no, like it's not hand designed by some god. Actually, Democritus is the first one. He called it atomos. He said like the world is made of really tiny particles, I think, and he named it atoms. Still he didn't have idea like how atoms look like now with super high resolution things and super nice optical developments. We can actually visualize how the atoms look like, how the molecules look like, and even we can go down to realizing how how the molecules how the molecule structure look like. But that time he realized this without even any observation. Then comes to Greek philosopher who really started the physics thing, I'll say, because he tried like, what is physics in my opinion? So the term physics, well, the modern trend of physics not always not always see what we physically see, but the term physics actually came from the the physics thing. So whatever we observe in the physical world, that's physics. So he tried to give how a look on how the physical world in the universe works, the motions of different objects, and he tried to give a formulation. Here I'll pose a question. So, well, physicists, and this is the first debate that comes. So, if you think of a physicist and the philosophers and the religious people, so what is the main difference that makes us physicists and not someone believer, not even religious belief? Even sometime I saw some scientists who become really believers. So what makes us different? If you look back to Aristotle's proposals, uh, are they all right? Like he proposed some stuffs, but are they all right? No, they are not. But he at least tried to know how the universe works, and then he proposed some stuffs, and these things later got modified, um, and we realized they are not all true. But still, he is called the father of physics. Then why is that? Because he tried to actually understand from the physical perspective, the governing law that's behind all of this. So that's where the main essence of physics, I think I'll say, that's the main essence of physics. Now comes now it comes to another interesting topic of science. So if you see a random animal building a nest or something, or even let's say like a beaver who is creating a nice dam for it, you will not see them measuring everything, even if they create some beautiful things. The architect, bird and all, they create some beautiful things, but they are symmetrical, they have a sense of symmetry, but they don't always have the sense of measurement. That's a nice thing uh, that human actually been able to realize that everything can be ruled down by some units. The first thing probably you learn in physics is units and measurements, and that has a reason, because we tried to measure the whole universe by quanti like we really tried to quantify it by some small units. And that's really impressive if you think of other animals. And then by these measurements which we tried to do, we actually try to realize how the universe works, and quantify some other stuffs or more complex stuffs. Like first we measured mass, and then we realized the force is mass into acceleration at some point, and then we developed measurement for force also, that we maybe physically can understand when you get slapped by a friend, or pinched by a friend, but then otherwise you don't always see them, but still we can measure some quantities like that. Next, this guy, this person needs an honorable mention in physics, Archimedes. So you have heard probably all the stories, like when he was running naked and in midst of the road, saying "Eureka, Eureka," because he understood something. So that's how science should be. You should never get bored of what you are doing. If you are reading physics, you read something to know something or to realize something. You never read something. Okay, for physics to get scores, probably you have to read something, but still you should have fun, like all these people had at that time. So he was really nice person to innovate super nice things, but it it deserves a mention that whenever humanity was in crisis, there are lots of development of science. Um, his major scientific development, that was liver, and he of course said he can even move the earth if he gets a huge liver, which was of course not true. He didn't realize that, but this liver system to form catapults and all, he was he invented it for the king, and it was for the purpose of war. So if you see the history of wars, a lot of a lot of scientific developments were done in time of wars, like all the atomic Oppenheimer project. If you know the infamous or famous Oppenheimer project, well, for humanity it was really scary time, but for science it was actually really progressive at that time. So a lot of scientific development actually comes from when humanity is threatened. And when I say war, I don't always say as in like really fight between two group. War can be against like coronavirus. Now it's going on. So if you look at the biological developments, the mRNA strains that are used, the trends, that is first in the human history, and it is done within 1 year. The mRNA vaccine, which is really another step to realizing how human body works. Um, and it happened actually in the war among human and the virus. So this is an example, and also you can think of like our environment is really changing, and we are not yet scared because we don't see the impacts that harshly. But probably when we'll be seeing the world really bad, we already started this steps to do a lot of scientific development to go to renewable energy source and all. That's a part of my work, by the way. And then we'll develop a lot of scientific things that are not yet known, and will I hope actually really will be able to do a huge change in this world how it's going on. So that's a philosophical view of me on wars and how humanity thinks. So yeah, the Archimedes he actually developed this lever system, and then he also proposed the theory of buoyancy, and then he actually proposed the laws of center of gravitation and balance, if you know. So he developed all these stuffs in ancient Greece. Then, of course, because of my Indian origin, I'll always come back to the Asian background, and we can be really proud of the work that was done in that time by Asian scientists. The first person who was in parallel, like, well, there were no Instagram, and ResearchGate that the other guy published, okay, I think that's a cool idea, so I take it and explore it more. It was not that easy that time. So Conrad is the first person to say in India that the world is, it seems like they are built of small particles, and it was 200 BC. Then Aryabhatta, he deserves a mention. He did so much great works in mathematics and of course in physics. So in ancient India, it was kind of obvious that Earth is rotating around the sun, unlike Europe, where it took much longer to actually throw off the idea that Earth is the center of universe. And Aryabhatta actually mentioned it in his work that Earth rotates around the sun, and so are some other planets. In ancient China, a lot of study was made in about magnetism, which was kind of gone and later got recognized by some other scientists. It was 4th century BC where magnetism was not really a thing um, for the Europeans or Western culture. Now comes to the transport of ideas, like how ideas can be transported. Now we have internet and all these cool stuffs, but at that point we didn't have that. We didn't have Facebook to update, okay, I think I am publishing this paper and it's super nice idea. And ResearchGate is basically Facebook of scientists, if you don't know. And then there are traders, they could take stuffs, of course, but they could also transport ideas. And that's why at that time, like in some sea, 100 C or something like that, Arabic people got really interested in science, and they explored a lot of scientific developments because they were the main traders in the route. So here, of course, Ibn al-Haytham, who is kind of modern scientific method of data acquisition, he's called the father. And even for experimental scientists, I think he was the first one who started scientific experiments in the ancient Earth. So what does actually it mean, like scientific method of data acquisition? It sounds so like all of these papers which you cannot really understand with the name, but then you realize, okay, he's trying to convince this. So data acquisition is collecting data. As I mentioned, human loves to do archive. They loves to keep their history. They love to mention it and continue so that their idea lives on. And that's why actually I think you keep your photos in all these social medias. Those are also information. We want to keep what we already had and make a progress. So data acquisition is basically when you record some scientific observations that you did and try to do it again, redo, and try to see if they are same or not. So that's why he's called father of modern scientific method of data acquisition, because he tried to observe different stuffs again and again, and he wrote it down how to properly do the methodology. Now, probably when you go to experimental lab, you go to do some experiment, and you say your teacher says, don't. Your professor says, don't only do only single experiment and say you are done. Try to repeat it, note it down in a lab book, show us the lab book. Uh, it's a boring process for you probably by now, but that is really important for scientific development. If you think it as keeping your old pictures to realize after some time how did you look 10 years ago, it's similar for science. Like what you observed 10 years ago, it's really fun to see, like uh, 10 years later, through the development how you are thinking 10 years back. And that data actually can make you realize something more. We'll come to the point where science actually comes back to life, some scientific development that got actually dumped and later came back to life, and people really recognized it later. uh, so this is an important realization, I'll say, for me, on the process of uh, data acquisition and science. So this is the theory of experimental reproducibility. What is reproducibility? Suppose you go to bazaar and you see this guy sits down with this kind of vegetables. One day you observe it, and then next day you don't see the guy. He went to the other place, and you see that he's selling the same kind of vegetables. But then what you can say is this guy actually sits down at this proper place of the market? No. But you can say, this guy probably produce, if he is a farmer, probably he produces these vegetables, and he brings them to market. So if you have concluded this guy always sits in the market in this place, then you'll be wrong. You'll be wrong to assume that. But that's where the repetition of experiment actually stands. Like you have to repeat some experiment again and again and again. And if it's true for all the cases, if you didn't do something wrong, then it's called reproducible, and then it's a general theory. Then I'll again go back to the progress of science and an honorable mention of Ibn Sina, who wrote a book about theory of motion. Remember, like Newton is still not there, so there is nobody to tell about how things move. Then he formulated the projectile motion in this book of theory of motion. He even he was very close to understand the force the air existed and how the force works, because he mentioned about something that basically resists the stone to freely move through air. So that's how the beginning of classical mechanical movements and classical kinetics started. We'll see how it actually evolved through Newton and later on the projectile motion theory, how it evolved in Europe, how it progressed. So then some other mentions, Omar Khayyam, who actually did a solar calendar, which was actually much more precise than the one used at the time, and later on even he proposed a particular solar calendar which was really precise with the measurement of how the sun moves on the sky. Then Abul Bakr al-Baghdadi, uh, so he really tried to continue the work of Ibn Sina, and then tried to propose the projectile motion in more precise way. And he is the guy who actually introduced the concept of power and acceleration. So he said, okay, Ibn Sina was right. The force actually works, and there is something that if you put more force, there is more motion. He was not clear about the word acceleration. He was not yet understanding acceleration as in the velocity can also change. But he mentioned similar stuff, and he actually got confused between velocity and acceleration, I will say. But still, he put some effort to realize how the body moves. And then that's a fun fact. So Ibn Baza, who was there, he actually proposed, oh, okay, so if you put a action force, like if you put some action, there will be a reaction force. But he is not never mentioned in modern literature because Newton perfected the theory, because he didn't mention about the equality of action and reaction force. Then I'll go to Nicholas Copernicus. You have all heard of him, how the Earth moves and planet moves on the sun. As I mentioned you, in ancient India, the things were observed much before. But then he said, like, okay, Earth and planets move around the sun, and he had a big fight with the churches at that time. Then this from this theory, I'll slowly go to the theory of planetary motion, how they moves, how gravitation works, how they realize. So Kepler, he observed the sky, he observed how things are moving, and from this observation, he proposed, okay, they are not moving in a circle; it's kind of in ellipse. It seems the planets, what they rotate around, they are in ellipse, and then he gave his planetary motion laws. Of course, if I don't mention Galileo Galilei, it will be dishonor to him, because he really fought for science and the convention of accepting everything that were there. Even some theory of Copernicus, which was not right, which was accepted later on by the church, but then he opposed and he experimentally proved it. And then the church was not agreeing with him, and he suffered the consequences. It's much better compared to the modern science. At least you don't have to get punished for saying, okay, you are not right, you are maybe this is the new theory. So this guy actually first person, this is the first scientist who proposed laboratory experiment. So he tried to observe things that are universal. Okay, we were looking at stars, we were looking at stones, but you can take the stone back to your place, you can throw the stone, and you can measure how far it moved. And that's where actually experimental laboratory experiments started to take place from this person. Now we are slowly moving to the really high acceleration of scientific progress, which came in the time of Newton. So Newton is the person who tried to perfect all the theories that existed, from optics to gravitation to laws of motion. So you all know the three laws of motion of Isaac Newton. You always thought like, yeah, there are first law, second law, third law, but we don't know where it come from. Actually, it came from all these past developments. He read through the history. He even took the idea of Ibn Baza, And then because the literatures of Ibn Bajjah was already available in Europe, and he perfected the theory. He tried to give a law which will totally explain all the motions. So he is the first person who says the relative motion and frame of reference, which is very important in modern days. But then it was not obvious at that time. Like, things are relative, it's not exact, like you are at zeroth position. So if I say, okay, I am at zeroth position and you are 70 kilometers far from me, it doesn't make sense. When I say 70 kilometer far from me, so I am the reference. But if you say, okay, you are 70 kilometer far from far, like you will not have enough information. So we always need the reference. And Isaac Newton is the one who mathematically formulated things for this. Actually, Rene Descartes, I didn't put his name, but it's lots of names. At some point, I realized I'm putting lots of names and I discarded later on. But Rene Descartes, Cartesian coordinate. So Rene Descartes is the person whose name is in the formula. But he actually took the idea of Newton and formulated proper idea for that. And what you see on the right is actually Newton developed. It's a reflection uh, telescope which he used, which he developed first and used to observe planetary motions, and then came to the theory of gravity ultimately. So now I'll try to say some things what he thought about optics. At the point of Newton, he thought uh, the light as particles which hits on stuffs. So later he discovered that in prism light actually gets dissociated, kind of. He mentioned that dissociated and creates different colors. So he mentioned there all these colors are inside this light, and from there on actually the shift from particle to wave theory started. But we'll here see like how science evolves, how physics evolves. It's not always constant. That's the basic moral you can take from science or physics. It's never constant. So what is light? At the point of Newton, as I told, it was particle. Then slowly wave was discovered, and then electricity was discovered. Thomas Alva Edison, his story of trying to make a bulb. Probably you have heard all the nice patents he had. He developed so many nice tools and bicycle. He tried to capture the electricity, and with the laws of electricity evolved, and then later on the magnetism evolved. We started to realize light is an electromagnetic wave. So then the theory was perfected by Maxwell. You have seen, all of you have seen these equations. So I can give you all these equations, but what does it actually mean? This theory is really interesting on the sense. If you carefully look at the first two equations, what do they tell about? They try to relate about electric field, what it tells about only electric field or magnetic field. But the third and fourth law, they actually combines the electric field and magnetic field. And this is the first approach or first step, I'll say, we take from Faraday or Ampere, that we try to combine things, we try to sort things down. Like electricity and magnetism, okay, we have two forces, but what if they're the same? And from this, the Maxwell equation came. Later on, the propagation of electromagnetic wave was realized, and then the electromagnetic theory, wave theory came, and we realized, okay, light is basically two oscillating waves. One is electric field, one is magnetic field. So the evolution of electric field creates the magnetic field, and the magnetic field creates the electric field. I'll not say create here. I'll more say makes sustain the other field, and that's how, without even a help of a particle, the wave can propagate through. So this was the electromagnetic theory of waves. People are happy. So light is no more a particle, light is electromagnetic wave, and we know everything. Then I skipped a bit of thermodynamics and of course fluid dynamics, a part of that. But then the thermodynamics evolved, the famous scientists Carnot and all, who tried to understand how the temperature, the heat of a body, how they work. And the ideal gas law came, Avogadro number came. We tried to quantify all the things that are around us. We tried to have a concept of atoms. We tried to have concept of molecules, and thus the thermodynamics propagated. The law of thermodynamics came, zeroth law came later, first law, second law came. And then by 1900, we said, we have a complete theory of science. We don't need to know any more things. We have a complete set of physics. So what are they? The classical mechanics that were developed by Newton, and all the mathematical tools were involved, and then classical mechanics was perfect. Then development of electromagnetism and wave theory, that we knew about sound, acoustic waves, and we knew about light, the electromagnetic waves. So we knew everything, and the thermodynamic laws. But then came theory of relativity. So this person, Einstein, how he started his job. He was not at all scientist in his job, and you have heard how he was scoring 3-4 out of 100 in mathematics. So he was not really a science person in the beginning. Later on, he developed a really interest in understanding different stuffs. And with the observation of light shifting through different stars, which he observed, he tried to realize, like, are there something we are missing? What if, like, what is light, and like, what's the motion limit of things? And then he came to the principle of relativity. First, he came to the relativity, which is called special relativity, in his paper. And then he said, okay, there are inertial frames of reference. So the laws of physics are same for all observers in same inertial frame of reference, but it's relative to one another. It seems very simple from our perspective, like what does it make difference? But then he put a limitation, which is speed of light is limit of everything. So there cannot be any speed that is greater than the speed of light in the vacuum. That changed everything. How does it change everything? Because if things cannot run faster than light, then imagine how many restrictions do it put. So imagine a light is running and an object is running to the speed of light. Then it will not be able to reach the light at any point, or like if they're running in the same direction, the information will never reach from one point to the point. If you imagine they both are in the same relative field, same inertial frame, then you can have an idea, okay, they are in rest with each other. But now what if they have a slightly less, one has a slightly less velocity than the other? Then everything again gets changed. One particle is running, one particle is running at speed of light, one particle is running at speed of 99% of speed of light. And still the information will take some time to reach. So imagine in between that, an information came through, like one put action. one body put action to one. So by the time the particle reacts back, the second particle, is it at the same position? If it's not, then if it moved, then because the information takes some time, it's at max speed of light, uh, then things are different because the position of the particle moved relative to each other. That means the direction of information is different. So if action force and reaction force are vectors, if the vector has a different direction, then they are not equal and opposite. That was proposed by Newton, and things get changed. So from this, the paradoxes appeared. You will know very soon about Lorentz contraction. So if something runs in the speed of light, you see them contracted. If you run in speed of light, your age, you don't age compared to a person aging on Earth or with non-relativistic velocity. So that develops some nice paradoxes which I recommend you to read about. They're super nice. And then came the theory of general relativity. So there are lots of general relativity theories, and they tried to perfect actually what are missing in the special theory of relativity. And there is so from this one first, the space-time concept started. So till then we said, okay, time is running, it's linear, and that's it. Time is running, we cannot catch it, it's everything, and like we have no control on time. But apparently these huge gravity pulls, they have control on time. So they can kind of bend time, and then because the light changes the path, so it's kind of changing the velocity of light, which is actually not changing the velocity, but it making a particular path where the time is bent and it's passing through that. So for the first time, we get an idea, okay, in the space, the time is kind of wrapped with space and very heavy things, which is really very compared to even our Earth can bend this time and space. So that now from that we came to general theory of relativity. I already talked about Newton's law, how in relative scale they were supposed to be flawed, and from that we again, okay, with the introduction of special theory of relativity and general theory of relativity, again things come to see, okay, now the theories are complete, we don't need to bother about anything else. Now this picture was not any more clear with the development of, actually the developments are going on when Rutherford actually developed the concept of electron and things. So Bohr, with the theory of Max Planck, tried to give an idea, okay, there are different energy levels in atom, and then with the energy difference between them, a photon can be emitted if there is a transition from this quantized energy states. So what is means by quantized? Quantized means they are not continuous. They are discrete. So if there are energy levels, and if one electron jumps from one energy level to another, it will emit a photon which has this gap of h nu, and then uh, everything is quantized, and the photons can only be emitted in this quantized form h nu. Now why does this makes everything different? It makes everything different because now he said the light can only be emitted in a quantized form h nu. So what is this quantized form? That means the light is basically a particle, which is a photon. We call it, like we call later on, it's a photon, and it's a particle. So now if you come back to Maxwell, like if you see back to Maxwell when he was so proud that he perfected the theory of light, he must be crying because now things are changing back to what Newton said basically. What Newton said about the light, it is a particle. So things are coming back to past. That's not right. So of course, at that time, the best two scientists, Planck, Born, Bohr. I'm getting confused with all these names. Bohr and Einstein, they had a really nice debate, and I think we should learn from this kind of scientific development that were going on that time and the relation between the scientists. Nowadays, if you see about the scientific community, if somebody proposes a theory that you don't agree, people start to cry like, "What is going on? That is not right." All, but Einstein didn't agree much with Bohr's theory, and he said no, the electromagnetic wave theory is super stable and light is never going to be a quantized thing. And then there was a huge debate, public debate between all the famous scientists at that time in Europe, and Einstein and Bohr participated in it. And to remind you, Einstein actually thereafter started to believe in the primary quantum theory, not believe or trust on the quantum theory. He didn't have trust at all. So that is a mentality I'll call a physicist mentality. You put question on everything that is coming, of course, but when you see the theory is much stable, much more stable to explain phenomena, then you have to agree even if you didn't agree in the beginning. Just to put another fun fact that I was reading through the paper of Planck, from where it started that a cavity actually radiates in a quantized manner. He actually tried to think as if it's a closed shell, a black body. It's a closed shell of radiation, and then it's kind of acoustic modes. So if you know acoustic modes, they are also they can only be formed with nodes and antinodes at a point, and so the black body radiation can only occur in these acoustic modes, which is, that's why it's still called acoustic modes, which has different explanation nowadays, but it's still called acoustic modes. Um, and then where the theory of discrete radiation came from. So he started from a classical approach, which is simple wave theory, and then he started in totally new genre of science, which was very interesting for me to read. Then we'll mention about Louis de Broglie. So I was reading about Louis de Broglie, and it struck me like he was not really a student of science. He didn't study even science. Physics is further. He didn't even study science. So his first degree was in history. Then he went to the First World War. After that, he sees new physical developments, and he suddenly was interested in his brother's work, where he was struggling. His brother was physicist, by the way, and then he put some simple logistics on it. He said, okay, you say an energy of a particle can be mv square, mc square. Any particle can be converted into a mass. A mass can be converted into energy equal to mc squared. That was already there. And okay, photon has some rest mass, and a photon which can also be converted into energy, and it can also be considered as a mass. So why not both? And he came with the theory of wave particle duality.
Bhagudai, please complete within 5 minutes.
Yes, sure.
Yeah.
So that's where actually the theory of wave particle duality started. Then I'll I'll briefly discuss about the Schrodinger's cat. Like you all know how we decide about whether it's dead or alive. Then quantum theory, the modern quantum theory started developing actually. And then what you can think it about is like if you taste a bit of your favorite cake, then the cake is now distorted. It's not the same cake anymore. So whenever we observe, we perturb the theory, and theory of perturbation came, and that's a famous dilemma that we have on physics. So I'll briefly go through. You know about Schrodinger's equation, but it's also came from a kind of physical perspective of classical mechanics. So it has a basically kinetic part, a potential part, and then it tries to equate with the time evolution. So it's not totally very new, but still it's very nice to create a quantum realization of the states with such classical view. I tried to brief a bit about how the theory of atoms, molecules, they become how they evolved, like from a particle pudding theory, then it's rotating around molecule around the center. Then the center is also particles. It came, and yeah, you know this famous development of Rutherford, which basically proved later on that there is electron, which was first considered as wave, which was considered as light, then it was a particle. Then Big Bang theory, of course, where from we originated. So I can come back to our start of the presentation, and I can say like what we realized probably 3,000 years ago. We formulated it at finally that we started from nothing. And yeah, so first thing probably now comes on the TV series, so I put an honorable mention. Then we actually tried to understand the universe altogether. So we have these four fundamental forces that we developed over time. Over time, we realized there are four major forces which are kind of different. Then we tried to even unify all of them. By now, what we developed is a standard model which could unify three major forces that are electromagnetic forces, weak forces, strong forces, but gravitational force still is not and uniform in the standard model. So by now we know probably this is very recent actually. One of my friends is also working. So this is a big detector, huge detector to detect a gravitational wave, which was still not proven, but very recently in 2014 or 12, I think it got proven that gravitational wave also exists, but still we don't know any gravitational particle. What is the moral from all this story that I told you that I learned is, okay, don't take anything granted, even if you have a simple formula or about, let's say, thermodynamics, about even Newton's law. You question them. You question how they came like in the beginning, how it started, and you question the validity of it, and you don't take it granted, and that's where the learning process is there. And if you see the example of how you can revitalize some old theory and they can be true, the new theories can be wrong, you can always learn from the past. That's why I thought like introducing this history of science, a brief history of science, will be very interesting for you. And I'll say enjoy more of your learning, and you try to realize what's the most plausible reason for what is going around us. That's it. Thank you.
Okay, thank you, Uday, for your very nice talk. Actually, the knowledge of development is always interesting. Uh, Actually, the knowledge remains incomplete if we don't know the how a theory is developed or why it is developed, what are the necessity of a theory, and so on. So it's very interesting. So any question, any comments from the audience, students? Please, if you have any questions, Anybody?
Hello, sir.
হ্যাঁ 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 বলো।
Sir, actually, Ahuda sir has told us that Newton was first realized that light, basically the flow of particle.
Hmm.
So Newton was a scientist in the century of 17th century and 200 years before Max Planck. So if Newton realized that the light is basically a flow of particles, then he was the founder of quantum mechanics. We must say that. Is it true?
Uh, that's a good question. I'll not say like I'm like what Newton did actually. Newton even developed the Newton circle of light. So he basically transitioned from particle to wave. I'll say he was not even like the linear optics that was there. It was in the particle form already. So he was still believing in particle physics, like optic. The light is particle, but still he was kind of transitioning. So he was halfway there. Uh, so the thing is quantum. What is quantum theory? Quantum theory is that energy and all these stuffs are quantized first of all, and then if we observe something, we can perturb the system, and we don't know the what state it was already in. That's where quantum theory actually lies. So I'll not exactly say Newton was the first developer of quantum physics. Like I cannot say like in the Vedas it was mentioned that things came from nothing. So the Big Bang, they were the proposer of Big Bang theory. When you perfect a system with your observation, then only you can claim the position. Will it mentions it needs an honorable mention, but you cannot call them the the creator of the science because they didn't realize it that way.
Yeah.
Yes, sir.
Any other questions?
Yeah, Abudai, if I allow me to ask you.
Yes, sure.
Yeah, Abudai, what is your research area, research topic?
So my research topic is spectroscopic diagnostics mainly, and I work in plasma physics. My interest is more on spectroscopic diagnostics than plasma physics. But I still try to realize mostly on plasma physics how reaction mechanisms are taking part, how the physical property of um, of the plasma is changing according to the optical diagnostics.
Okay. So it is not exactly that plasmonics optical people used to work. It's not the same area, right?
No, in plasmonics, it's more quantum theory of plasma.
Yeah, of course.
Uh, it's more particle approach, I'll say. Uh,
So you're
my
talking about bulk plasma, right?
Yeah, it's
You're
bulk
working
plasma.
bulk
It's
plasma, right? Okay, okay,
yeah, yeah.
okay. Okay, good. Nothing else.
Thanks.
Okay, if there is no more questions, then we should thank again Ahuday